All right, so we're going to do hypothesis testing for Unit 5. All right, guys, up here. We're going to look at hypothesis testing. It goes along the same lines as confidence intervals. So if you were like, I liked confidence intervals and understood them, that bodes well for you with hypothesis testing. Okay. And if you didn't like confidence intervals, well, then this is an opportunity to sort of review some of that, okay? All right, so what is a hypothesis? It's a claim made about a population based on the results of a sample. Slightly adjusted a file. Hold on, let me open it. Because yours doesn't say this next, does it?
Yeah.
You have different, yeah, okay, hold on.
Written number 4.
All right, hold on, we'll get there. This is what happens when I edit. Give me a moment, talk amongst yourselves. Okay, I'll rewrite the top part. So a claim made about a population based on the results of a sample. Okay. All right, so we're going to start talking about different types of hypotheses with this. You're going to write a null hypothesis and an alternative hypothesis. So what your null looks like is H sub 0, that's your null. And it is either going to be, if it's a proportion, it would be the parameter, so the population proportion. And I'm just making up an example here. Equals, we'll say 0.9. If it's a means, you would say mu equals, I'll say 10. Okay, I'm just giving you random numbers. So your null will be one of those two. It's not going to be both a proportion and a mean. Okay, one or the other. And that always comes from the parameter. Okay, it's not x bar, it's not p hat. It's p and mu. It will always be that it equals some number or proportion. Okay. Your alternative hypothesis, that's H sub A, still sticking with P and mu, but it's basically any inequality that you could write. So it could be P is less than 0.9, or you might have P is greater than 0.9, or you could even say P does not equal 0.9. Or the same thing with mu if it's a means problem. We could say mu is less than 10, mu is greater than 10, mu does not equal 10. So the null, you're always going to have an equal sign. Your alternative, you'll have an inequality. Now, based on the context of the problem, that's how you figure out, is it less than, greater than, or not equal to. Okay. All right, you always want to talk about the parameter that you're investigating, like what is the mu or what is the p. You would define that at the beginning of your test. And you have to pick which type of test you're doing. So just like with confidence intervals where you had to pick means or proportions, it's the same idea with hypothesis testing. You have to pick, is it a mean or a proportion? Is it Z or T? How do we determine Z or T? Yep. So sigma known or unknown? Sigma known, that's for Z. Sigma unknown, that's your t-test, okay? So all of that stuff is the same as it was in the last unit. The y is capital T. Yeah, Madison.
What's an example for number 2? Like the define the parameter.
So you might say, like, the mu is the true average number of hours students spend studying for a retake. It's just like whatever the population.
So it's kind of like in our past data journal when we had to like explain, define the population.
Yes. Yep, very similar to that. Okay, and then the last piece you have to decide, is it one tail or two tails? That's where this inequality comes from. So if it's less than, let me draw a picture for each of these. If it's less than, you end up with just this tail that we're talking about. That's what a less than picture looks like. Greater than would be over here. What do you think not equal is going to look like? Not equal to. Yeah, what do you think? Exactly, yeah, that's the both ends of it. So this is what they're talking about when you're asked, is it a one-tail test or a two-tail test? The not equal to, that's the two-tail, because you have both tails of your distribution there. And then greater than or less than those, you just get one side of it, one tail. Okay. We're still checking conditions, and those are the same as your confidence intervals. And we'll do that when we do some examples here, but it's still the random sample and then normality. And step 5, you do math. Really, your calculator does math for you. You're going to find whatever the test statistic is that you're looking for, and your calculator is going to do all of that for you. We're going to write down the formula, but I wouldn't expect you to do them by hand. There is, you know, on your calculator, you've got tests. That's where all the hypothesis tests are. So we'll do that on your calculator. And then graph distribution, mark test statistic, and calculate p-value. That just means make a sketch. Like draw a little picture for me. And then write down the p-value, which you're going to get from your calculator. I know you don't know what a p-value is yet, but that's okay. Then as you get to writing your conclusion, you compare your p-value to the significance level. So every hypothesis test you do has a significance level, and that's our alpha level. Usually 0.05 is what you want to use. If it's not stated, you would assume that's the alpha level. But certain tests will tell you use an alpha of 0.1 or use an alpha of 0.01. It depends on how precise you want the hypothesis test to be. Can you think of what that might be connected to? What an alpha level of 0.05 might be connected to that you already know? Close, like you're thinking of the right thing. Yeah, Josh?
Like a 90% confidence interval.
Mm-hmm. Yep. It's connected to your confidence level, okay? All right, and then your contextual conclusion. When you do a hypothesis test, just like with your confidence intervals, it's a very sort of canned response and you just fill in the context and your numbers. It's all about if you're rejecting the null hypothesis or failing to reject the null hypothesis, okay? And we'll do examples with that. You'll see how it works. Questions so far? I know it's kind of just spewed a lot at you there, yeah, Maya. What do you mean, sir? Yeah, so that comes into play if you're rejecting your null. You're testing to see if the alternative is likely to happen by chance, like if something different than what your null is could happen. And it all depends on, you know, running the sample and all of that. Yep, they always will come in pair. Yep. All right, let's look at one so you guys can kind of see how all of these pieces work. Sorry. There we go. All right, let's read about company and their chips. All right, so they claim the mean weight of their bag of chips is 120 grams with a standard deviation of 12 grams. Tyrone is skeptical. He feels like the company might be underfilling their bags. And this is too high. He took a random sample of 49 bags from the company and found the mean weight to be 117.5 grams per bag. We want to know, is there enough evidence that the company is lying about how many chips are actually in their bag? So what we're looking at, they're claiming that the truth is 120 grams per bag. You're going to do a hypothesis test to see if there's enough evidence to reject that claim, to say, hey, they are lying. Okay, that's what you're testing. We got to know if we're getting shortchanged on our chips here. Okay, we don't want to be. All right, so first we have to decide, is this a means or a proportion test? Means, yeah, you see mean weight. That is a clue. So means. And do you think it's a Z or a T? It is a Z. They tell you the standard deviation is 12 grams. So that's kind of, all right, your brain is now narrowed down to we are only looking at means and Z. Now, what you'll want to do on your test is actually name the type of hypothesis test you're doing. And just saying a means for Z is not quite enough. We would call this a one sample Z test for means. Right now, you're only learning about one sample test, but later in the year, you're going to learn about two sample tests. So we have to identify not just that it's a Z test for means, that it's a one sample Z test for means. Okay? Get in the habit of putting that in there. You can also identify it by formula if you write the correct formula. So if you're doing one of those two things, that will help you with points on your exam, okay? All right. What are we talking about here? What is the true parameter that we're investigating? Yeah, go ahead. Yeah, so what we're caring about is the mean weight for these bags of chips, right? So you would identify that. I'm just going to write it at the top here. We are investigating the true mean
Is this the defining the parameter?
Yes, this is the defining the parameter. You could even say like mu equals the true mean weight for these bags of chips, you know. So that's the mu that we're talking about. All right, we're going to write our null and our alternative. Okay, we know the null will have mu equals in it, right? What is this company claiming that mu equals? Yep, I'm going to say mu equals 120. Now, if you didn't define the parameter up here, like, hey, this is what we're talking about, what mu represents here. In your problem, you would want to write your null and alternative out in words. I much prefer to just write it once instead of with both hypotheses having to write it out with, we're saying mu for, you know, the true mean average of weight for bags of chips is 120 grams, and then writing that all again for the alternative. Seems like too much writing to me. Okay, your alternative is going to be an inequality. Do you think it is mu is greater than 120, less than 120, or not equal to 120? What do you think, Gabby? Gabby says less than. Yes, she is correct. Okay, so let's talk about that. The company claims it's 120. This guy Tyrone thinks he's getting gypped on chips, right? If he is getting shortchanged, that would mean that he thinks the true mean is actually less than 120.
What you're kind of proving is the alternative.
What you're like testing and checking for, yeah. Now, a lot of the times, not every time, but look at your sample. Our sample mean was 117.5, right? That is less than 120. It's a good clue that we're probably testing that this is less than 120. It won't always work out like that, but most of the time it does. Like your X bar can kind of guide you with what your alternative, what you're looking for there. Okay. All right, let's also check our conditions right here. All right, what do you think about simple random sample? Stated, yep. He told us. I took a simple random sample. Okay, normality, normal condition. What do you think? Greater than or equal to what? Yes, it is 30. The 10 is if we're doing proportions, okay? So yes, our sample size is 49. 49 is greater than or equal to 30. So what is that called when we have a large enough sample? CLT. Now guys, can I use CLT in a proportions problem? No. A lot of you did in this last test. On your conditions checking, you even went through and did like the n times p, and you wrote out all the work, and you checked that, and then below it you wrote CLT. No, okay? It's not CLT when it's proportions. CLT can only be used for a means problem, okay? All right, we need to make a sketch. So I'm gonna draw a little picture. what's in the center of my distribution? What are they claiming? Not quite. It's their claim. Yeah, what is mu? That's what always goes in the center. 120, yes. And then what did we find for x bar? Yeah, that's the other piece that goes on there. So this is our 117.5. And our alternative helps us see what we're shading. We said less than this, so we are shading to the left of our mean. We're finding that shaded area. What that area tells us is the probability of this occurring. So is it very likely that we would get a sample of 117.5 grams per bag? Like, that's what we're going to find out. We're going to calculate that area and see, like, oh, yeah, there's like a 23% chance that you could get a sample of that size. That seems pretty likely. The truth is probably 120. But if you calculate it and you get like a probability of, 0.2% that this could happen, that's really unlikely if 120 grams is the true mean. And so that's where we get into our conclusion. Okay, so let's figure out how to calculate this. We still want to write out what we know. Just list it so you've got it all when you go to do this on your calculator. We know our sample size is 49. We know our x bar is 117.5. We know our mu, 120 grams. And we know our sigma is 12 grams. Okay, does anybody remember how to find a z-score? From what, I feel like it was in unit, maybe beginning of unit 2, yeah.
And it's no longer the side. Oh no, that's
No, I know what you're thinking, that's fine. Do you guys remember the formula for just a z-score? Anybody remember it? You guys are like, what is the z-score? What's happening? Ryan, you remember? You forgot one thing. You're really close. It's over the standard deviation over your sample size, the square root of that. We were always using a sample of size 1, so it didn't matter. Now it does matter. So we're going to write down the z formula. So Ryan had it right. It's x bar minus mu, so your sample mean minus the population mean, over sigma over square root of 1. You're definitely going to want to write this formula down. You do not have to do it by hand, though, okay? We're going to do this on your calculator. What you could do if you did it by hand is get your z-score and then do the whole norm CDF to calculate the area. You guys remember a normal CDF? Yeah. But we're not going to do it that way. Let's get out your calculators. I'll open up mine here. Okay, any guesses where we're going to go to do a hypothesis test? Stat test. Crazy idea, right? Stat, arrow over to test. We have a lot of tests to choose from here. You can see we have a lot of those 2 sample ones later and proportions. What do you think we want, though, with what we're doing in this problem? This is just a basic z-test, right? It's not proportions. It's not 2 sample. It's just a 1 sample z-test. So we're just going to pick z. Hopefully this is what comes up. And you have two choices when you're doing these hypothesis tests. You can put in data, which means you know mu and sigma and all of that. Actually, I'm sorry, data is the one with your list, as you can see L1 in there. So let's say you had, like, do you guys see the problem if you turn the page where you've got all those values? If you would put all of those in list 1, you would then be doing it in the data method because you've got a whole list of data to use. We do not have that. We have stats. So let's go ahead and pick stats. And hopefully you have all the information you need for this. So what is mu? What is sigma? Good. What is x bar? Good. And n. 49. Okay. Then you have to pick which of these inequalities we're using. Are we using not equal to, less than, or greater than? Less than, so I pick that. And guys, don't pick just calculate. Go ahead and pick draw. Yes.
Mine keeps saying
Okay. Yeah, if you're not getting that for draw.
Thank you. That's just like. Anything else? Okay. All right. You're going to want to jot down both of these numbers from your calculator. So the z right there, that's your z-score, if you had plugged in those numbers to your fraction. And then the p, that is the p-value. That is the area, the shaded area under the curve there. Okay? So we need
both of those numbers. So I'm going to say z equals negative, is it 1.458? Is that right? Okay. And then the p-value was 0.072. Okay. So it's saying there's about a 7.2% chance of obtaining a sample with a mean of 117.5 grams if the true mean is 120. Now, 7.2% isn't a large percentage, but we're going to compare it to an alpha level of 0.05. That's the significance level we talked about just a little bit earlier. It is not stated in the problem what significance level we should use. If it's not stated, you pick alpha of 0.05. So I'm just going to kind of write that off to the side here. Alpha 0.05. We're going to use that. It's a weird looking alpha, sorry. Okay. Is my p-value greater than or less than my alpha? Greater than. It is bigger. So what we do with that in our conclusion, we say since our p-value of 0.072 is greater than alpha of 0.05, we fail to reject our null hypothesis. There is not enough evidence to suggest that the true mean weight chips or chip bags is less than 120 grams. All right, I'll let you write it and then I'll explain it. If you can't read something, let me know. I find I never have enough room to write up here, so I'm smushing it together. Okay, so what you're looking at here, you're always comparing your p-value to alpha.
When your p-value is bigger than alpha, you fail to reject, always. Okay, that's saying we're looking at this at the 5% level. If there's more than a 5% chance that we could have had this occur by chance in our sampling, we don't reject the null. We're like, yeah, that could happen. Even though 5% is not that high, that's what we're using as our level for rejecting or not rejecting. If your p-value is less than alpha, that is when you reject the null. That's when you can say, hey, there's a whole bunch of evidence saying this is not actually the truth, and go from there, okay? So let me just, to make sure we've got the difference there, when we reject and when we fail to reject. I don't know if you'll have room to squeeze it in there. You can always write it on the back of an assignment sheet or anywhere that you've got a little bit of room. So let's look at it a couple of ways. If alpha is 0.05, the p-value is 0.02. .02 is less than 0.05, right? Meaning my p-value was less than the alpha. When that is the case, that is when you reject null. This means there is evidence. Jot that one down, and then I'll write it the other way too, just so you've got it. I know it's a new concept that you're trying to understand there. All right, let's stick with alpha level of 0.05, but now let's say our p-value is 0.2. 0.2 is bigger than 0.05, right? So our p-value is now bigger than our alpha. So when that's true, what do we do?
Fail to reject.
Yes, we fail to reject null. Not enough evidence, okay? Questions on that? We'll do a lot more practice problems with hypothesis testing, but that's the basic idea. Yeah.
So, would the P equal, like, mean that is stated? Like,
Does what equal it? Sorry.
sorry, I'm having the P should be 120.
So the mu was 120. And then
The p-value changes based on
the p-value is like this shaded area under the curve. It's like if it ended up shaded all the way to here, your p-value would be 0.5. Okay? It's like how likely it was for your sample to occur. And that will change in every problem. And it's all based on how likely it is to occur given that whatever you stated was the mu or the p, if that's actually the truth. Yeah. Yes.
So in this problem, it's how likely the chip bag is to weigh less than 120 grams.
Yeah, so specifically to weigh 117.5 grams or less, essentially, is what we're talking about. Okay? It's like up to that little barrier. How likely is it for that or something more extreme? So 117.5 or less than that. Okay. It takes a little time for it to sink in. Like, what are we saying? What is p-value? There's a lot of new stuff there. Okay, we're actually going to stop there with notes, guys. Or did you have a question?
The basis is for all, and then do a blue one, so it's like.
So you're going to want to write it down in every single one, but you can do the test on. You can actually do the whole hypothesis test later. But definitely be aware of this formula, and same with a t-score. It's the same except you have S instead of sigma.
Do you have to write anything about the hypothesis?
Do you have to write anything about it?
Yeah.
Nope. You have to state it initially, but it doesn't really come into play with your conclusion. If you reject the null, you might say something about your alternative, but it's really just evidence to show if you think the null is true or, hey, we think it's maybe not true. Okay? All right.